Okay, today we're going to begin talking about electricity. Now, in this course, we've discussed energy and what that actually means, especially in terms of how it relates to sustainable energy. And most of the time, when we discuss sustainable energy in the modern world, we're talking about electricity as a form of energy. But remember, there are other forms of energy, mechanical energy, and we would call electricity, most often we think of it as a secondary form of energy. You take mechanical energy, you convert that to electricity. So let's discuss electricity now. And before we get into the ins and outs of electricity generation, let's take a moment to consider what exactly is happening when electricity takes place. So we'll do a brief little overview explaining what is electricity, a little bit into the history of how it was discovered, and how we can think about it in scientific terms, kind of from a physics perspective. Now, of course, this subject could get very complex. My goal here today is to provide a brief overview for you. So when we discuss electricity generation, we know a little bit more about what's going on. So here we go with a little brief overview of electricity. And we call it Electricity Explained. And take a look there in the beautiful image. We've got a lightning bolt striking over downtown San Diego. Lightning up in the sky is kind of our natural observation of electricity in the modern world. Although electricity is virtually everywhere, it's not really abundant, and it's definitely not something we can control without generating it. So it took a long time for people to understand what is it and how does it work? What are its physical properties? So what is electricity? A simple definition is that electricity is a form of energy that results from the motion of electrons. Remember that energy involves motion, and normally we think of moving from like a mechanical perspective, but electricity is when electrons are moving through a material. And electrons, as we probably remember, are particles in an atom. And you can see kind of the classical model of the atom as our central image there. We've got a nucleus in the center and electrons that orbit, or they more or less exist outside of the nucleus, and they're held together with atomic charges. Those electrons, as we may or may not remember, can be added or subtracted from the atom. And when that happens, it creates a movement of electrons, and that form of energy that results from the movement is called electricity. And electricity, of course, is very essential for powering our modern world. And it even powers our bodies. Our brains operate on electrical signals, our nervous system. And we can find evidence of electricity all over the place. So it's very important and quite mysterious because we don't have all of the senses required to observe it directly. So sometimes we have to do some experiments in order to see, study, measure, quantify electricity. So how did they ever come about figuring that out in the first place? Well, it's kind of argued on who was the official person to first understand and we could say discover the phenomenon of electricity. A lot of people attribute credit to Thales of Miletus, who was a Greek philosopher, and he was known as one of the quote unquote legendary 7 wise men of ancient Greece. He may have been the first human to study electricity about 600 BCE. Now, where is Miletus? That is in ancient Greece, in modern day Turkey. So a philosopher who lived in a prosperous city on the Mediterranean in the modern day country of Turkey is said to be perhaps one of the first people who studied electricity. How did he do this? Well, the story goes that he took a piece of amber, and amber is fossilized tree resin. And there's an image of amber there. It's that golden stone, which originally comes from organic matter from trees, tree sap, tree resin. So Thales took the amber and he rubbed the amber with fur. And by doing so, he was able to attract dust, feathers, and other lightweight objects would stick to the material. And you may have experienced something like that when you rub a balloon on your head and you watch the hairs stand up on your head. So what was Thales doing? Of course, he was playing with static electricity. These were the first experiments that are recorded with electrostatics, which is the study of static electricity. In fact, the word electricity itself comes from the Greek word electron, and electron in Greek means amber. So that's where we get the name electricity. It comes from the Greek word for amber, electron. And that goes back to the original study of electricity using amber and fur to create static electricity. And then we can fast forward in time all the way to the 1600s, the 17th century, and an English physician named William Gilbert, who was an amateur scientist. He began to study magnetism and static electricity. He repeated the research of Thales of Miletus and expanded upon it. He noticed that one object would attract or repel the other, and is given the credit for coining the term electric in this case to describe the forces that are at work. And William Gilbert resembled this movement to the movement of a fluid from one object to another. Even though there was no understanding of electrons in an atom and how that all works, seems like there's a mysterious fluid going from one item to another. So in the next century, in 1729, an English scientist named Stephen Gray observed that certain materials, such as silk, didn't conduct electricity. His explanation was that the mysterious fluid could either travel through objects or be prevented from traveling. And scientists even built jars to hold this fluid, quote unquote, and study its effects. Dutch instrument makers created what is now known as a Leyden jar, which is a glass jar containing water and a nail that could store an electrical charge. And so you can see a few images on the right-hand side of Leyden jars, what they are and how they work. And you can see that with some metal coating, glass jars, a metal rod, and a chain that's suspended in the water, you can end up with a positive and a negative charge of materials, and electrons will flow through there. They didn't yet know what it was. They were just trying to kind of capture this fluid. The diagram on the bottom shows how you could attach multiple Leyden jars together with a wire, and you could increase the amount of electricity that flows through it. In fact, the first time the inventor used this jar, he received a massive shock, an electric shock, static electricity. And this person got a big jolt from their Leyden jar. This brings us up to 1752, which is the famous kite experiment run by Benjamin Franklin that proved that lightning was electrical in nature. Benjamin Franklin also presented the idea that electricity had positive and negative elements, and that the flow was from positive to negative. About 30 years later, a French scientist named Charles Augustin de Coulomb conducted several experiments to determine the variables affecting an electrical force. His work resulted in Coulomb's law. And Coulomb's law states that like charges repel and opposite charges attract with a force proportional to the product of the charges and inversely proportional to the square of the distance between them. Oh my goodness, what the heck does that mean? We'll take a look at the image on the bottom right, and that is diagramming Coulomb's law and putting it into a mathematical formula. So as the charges increase, or the distance between charges increases, the force that either attracts or repels them will be altered, according to the formula described in Coulomb's law. Don't worry about understanding all the variables, but this is just a person who took something that's a natural phenomenon and made it into something that could be measured and therefore studied. It wasn't until 1897 that scientists discovered the existence of electrons. And this is where the modern era of electricity starts. And now we see on the right-hand side that classic diagram of an atom. Now, modern science may render some of this obsolete, or at least not completely accurate. But this is the classical model of an atom. And from an electricity standpoint, the concepts that we can understand with this classical model are useful. So this is a good model for understanding electricity. It may not be a good model for understanding other things in the universe. Quantum physics kind of changes our understanding here. But in general, with an atom, we have a nucleus. That's the center. It's made up of protons and neutrons. And then surrounding the atom in various orbits are electrons. Now, electrons are the negatively charged particles of an atom. Protons would be the positively charged particles of the atom, and the neutrons are neutrally charged. They don't have a charge, but they do affect the mass of the atom. All matter is composed of atoms, so everything you know, see, touch, feel is composed of atoms. And when an atom has an equal number of protons and electrons, then that atom is said to be electrically neutral, because the balance between positive and negative charges is the same. It's going to be a zero balance. Positive and negative balances itself out. Now, some electrons orbit close to the center of the atom, so they're closer to the nucleus. And these electrons are held tightly. The force that holds them in is strong. Wood, glass, plastic, ceramic, air, cotton. These are all examples of materials in which electrons stick with their atoms. Because these atoms are so reluctant to share electrons with their neighbors, these materials can't conduct electricity very well, if at all. These materials are electrical insulators. And so you can see the image on the right-hand side showing an extension cord. And if you cut the extension cord open, what do you find? You find a couple of different wires, oftentimes 3 wires, but certainly 2 wires. And those wires are made of metal. But surrounding the wire is an insulator made of a material that does not conduct electricity very well. And in this case, the insulators around the wire are made of plastic. Most metals, however, have electrons that can easily detach from their atoms. These are called free electrons. The loose electrons make it easy for electricity to flow through these materials, so they're known as electrical conductors. The moving electrons transmit electrical energy from one point to another. And this movement is what we actually call electricity. So now notice the diagram on the right-hand side. You can see basically an explanation of how there's an electron, and in this case, we'll say it's a metal atom, that it doesn't hold on to the electrons as tightly. And there is a free electron that will jump from one atom to the other. And that's why this material is called a conductor, because electrons can flow freely between the atoms in the material. And if we took that material, as in the diagram below, and we stretched it out in a line, we would create a wire. And we could get electrons to kind of move in one direction according to their charge. And we could harness the power of moving electrons. And that's basically what electricity is. It's the electrons moving down a wire through a conductor surrounded by an insulator. So let's explain that in a little bit greater detail. Now, each individual electron typically does not move down the entire length of the wire. Basically, it is stimulated and jumps from one adjacent atom to the next. When one electron jumps to its neighbor, it causes that neighbor to shed an electron, and basically it hops in a chain down the line through the wire. It has been estimated that 1 cubic centimeter of a substance contains 1 septillion electrons. And I wrote out the number there so you can see what 1 septillion actually looks like. It's a huge number that you probably cannot fathom in a small material, a cubic centimeter. Only about 1% of these are free electrons, but that is still 10 sextillion, and so we can still have plenty of electricity moving through a good conductive material. And they move at the speed of light, which is 186,000 miles per second. Again, a number so big and a rate so fast, it's hard to fathom. The speed of light is the speed at which electricity is flowing through a conductive material. Now, when electricity travels down a wire, that is the flow of electrons, and this flow of electrons is called current, kind of like a river. It's gauged by measuring the number of electrons passing a certain point in a given length of time. The unit of measure for this current, this flow of electrons, is called an ampere, or for short, we just say amp. And how exactly does this current move? Well, the source of electricity must have 2 terminals, a positive terminal and a negative terminal. In this case, let's check out the image on the right-hand side showing a battery as the source of electricity, and that we know has a plus side and a minus side, positive and negative. The source of electricity, whether it's a generator, a battery, or anything else, it will want to push electrons out of its negative terminal at a certain voltage. Notice the arrows, the direction in which the electrons are moving through the wire goes from negative to positive. These electrons will need to flow from the negative terminal to the positive terminal through a copper wire or some other conductor. And the path from the negative to the positive terminal is called a circuit. So once you hook a wire up to a battery, you've created a circuit, and electrons will flow through that material due to the positive and negative charges in the source, the energy source. And then notice that there's a simple circuit with a light bulb, a classic style light bulb, incandescent. And what happens how does the light turn on? Well, the electrons go inside the light bulb and flow through a little wire inside the light bulb. That wire is not as conductive. It kind of resists the flow of electrons, and when it does, it creates friction, which makes heat. That heat causes that wire, or we call it a filament, to glow, and so the light turns on because the filament is glowing with the heat from the friction of the movement of electrons in the wire. And we can thank Thomas Edison for that invention, using electricity in order to do useful work. So there we go with just a brief explanation into electricity. What is it? How did we figure that out? And how do we use that from a physics standpoint in our modern world to do useful things? From here on out, we can talk about electricity generation and the various methods for generating electricity. But remember, it all comes down to sending electrons in a flow, a directional flow through a wire, and that can be harnessed to do all kinds of valuable, useful, and hopefully efficient work in our modern world. I hope you enjoyed this little overview of electricity, this brief explanation. Maybe it gives you food for thought. I certainly encourage you to do some extended research if you find this subject fascinating. Hop into an introductory physics course in college if you want to learn more. And from here, we're going to take this basic understanding of electricity and apply it to all the concepts of electricity generation from a renewable, non-renewable standpoint, and trying to decide how do we find the most sustainable option in our modern world. Thanks a lot.